Hello, this is the first lecture in Introduction to Digital System Design, and in this very first lecture, we will try to give an understanding of where digital design is positioned and what part of digital design we are covering in this course and what is digital system design all about. Okay, and so the whole lecture is very abstract and covers the basic terminologies and things that as we go through the details of the course in the later lectures, we will be figuring out some of the details of what we will cover here in a very abstract fashion. I'm calling it switches to systems. The reason I call this, I use this topic is when you design a digital system, you design at a high level. You say, for example, that I have a vehicle detection component, the vehicle detection system that is checking the camera in front of my car, and the camera, the image is taken, the image is traced, and this is the system. And analyzed, and eventually you will know whether there is a vehicle in front of you or a person in front of you. Okay? But then, this is the system level way of looking at it. But when you get down to it, you get down into the details of it. All there is to it are a bunch of transistors, millions and millions of transistors. Okay, that's why I'm saying from switches, transistors. Okay, same thing. All I'm saying here is that from switches, those elementary basic elements, how do we go to systems? How do I take a system description like a vehicle detection and eventually bring it down to these switches, these transistors? Okay, so what we really need to know is what is between this system level and these transistors. Okay, what design steps do we have to follow in order to take one application, such as vehicle detection, and eventually bring it down to those little transistors? Who helps us in this journey? Okay, we have tools, we have simulation programs, analysis programs, verification programs, synthesis programs that help us perform this top-down transition. Okay? So let's look at some of this, and then we kind of try to highlight the area that this introduction to digital system covers. Obviously, we are not going to be able to design a vehicle tracking system by the end of this course, but we will definitely be prepared for it. Okay? So I will talk about hierarchical system structure, meaning, the hierarchy is at the top level is system. Then what are the components of the system? What are the components of the system? And then eventually the components of the system become those little transistors. And then we say, well, going through this journey, somebody has to help us. And that somebody is a computer to help us. The computer has to help us analyzing our circuit, synthesizing our circuit. But then we have to communicate with that computer. In order to communicate with that computer, we have a language. And that language is Verilog. And therefore, in this course, this basic elementary digital logic design course, Verilog plays an extremely important role because we have to learn logic, we have to learn Verilog. because that's the only way that we can deal with large circuits that we will be designing eventually. So Verilog is for analyzing, simulating, synthesis, verification. If you have a design done in Verilog, you have to be able to test it before you take it to manufacturing. Before you synthesize it, you have to test it. Well, but the circuit is not real, is a model of something that you like to be able to design. And therefore you have to test it. The same way a circuit is a model, let's model our test bench also in Verilog. We will be also talking about this. When you look at the hierarchical system structure, this is the same example that I just said. You have vehicles going around, and you have this camera in front of your car detecting these cars in front of you. Some of them are moving. You can an ADAS system will be able to track a vehicle, detect a vehicle, and so on. Okay, so that's the hardware we eventually have to design. And so what do we have? We have sensors like radars and cameras and things like this to be able to take the image, which is always an analog picture. That picture has to be processed. Now we are getting into digital. Okay, that picture has to be processed pixel by pixel. Okay, and therefore, it is the camera, and therefore that processing has to go into a digital component. And that digital component has a processor, several interfaces, perhaps a memory, perhaps some accelerators, perhaps an image filtering component. Okay, but all there is to it is a digital component. The CPU, filters, so that the things you don't need in the image, the color is not needed. Okay, so those will be filtered out. And then perhaps the boundaries of the vehicle in front of you is more important than the body, the full body of it. Perhaps you want to know if this vehicle is inside the street lines. Okay? And therefore, all of these are little hardware components that are put together to eventually be able to tell you that, yes, indeed, there is this vehicle in front of you, and this vehicle is moving or not moving, or moving to the right or moving to the left. The digital components are, like I said, some memory, some CPU, and then some little processing elements. Each processing element, let's zoom on these processing elements. Okay, each processing element down here is responsible for something. One is responsible for filtering the colors. One is responsible for being able to distinguish the street lines. And then some of them are responsible for other things. The whole thing is controlled by the CPU being the processing of this. We refer to it embedded system. Okay, we are not going to be able to do this by the end of this course, but we will be able to go inside the processing element and say, well, this processing element has these sub-little components. And eventually, those sub-little components become the transistors. Something like this, okay? Take one of these processing elements, and inside that processing element, you have, let's look, you have adders, multipliers, selector logic, This we refer to as register transfer level logic. Okay, so instead of saying that I have a filter, I say, well, yeah, there's a filter there. But then how is this filtering done? Filtering is done by multiplying something by something, subtracting something from something, multiplying an array of a filter by an array of an image. All of these become, look at the components I'm talking about here. All of these components become multipliers and adders and subtractors and things like that. And then in this course, yes, we are not going to be able to show you the filtering processing element, but we will be able to show you the multiplier. We will be able to show you the adder, the subtractor. We will be able to show you the multiplexer that selects this or this input. Okay? Once we understand this, once we see these little components in terms of those little transistors, then we say, well, the same way we put these little transistors together to build an adder, to build a subtractor, to build a logic selector, the same way we can take these multipliers and adders and things to put these together to build a processing element. And then the same way we learn this, we put these processing elements and the CPU and the memory and things into a vehicle detection component. Okay? So, where are we focusing? We are focusing on this side, on this end of it, because we are just starting. All right. If you look back at many years, it wasn't like this all the time. It used to be that you had a little design to do, and then you would actually do the layout of the transistors yourself. You put one transistor on top of the other transistor, connect this transistor to this transistor, and on and on. Okay? But then, when transistors become 50, 20, 100, 5,000, fine. But then when transistors start going into 10,000, 20,000, you cannot do that. And then what you do, you go one level up. You go from transistor layer level or layout level up to the gate level. And then you put gates together. You're quite happy. You put gates together and build things. You're good until the number of gates start getting out of hand. Okay, that becomes years 2000. Then you say, well, I'm tired of putting these little gates together. Let's do something else. Let's take higher level components. Then you say, well, let's take adders, comparators, registers, and put these together to build a system. This is called RT level or register transfer level. And this is good for a few years, but then becomes 2010 and beyond. And then you say, well, RTL, there are too many components. There are too many adders and subtractors and comparators and registers, logic selectors for me to put together. So let's go one level up. And that is ESL or electronic system level. This is all very good. But what do we do in this course? We do a little bit of transistor, all the gates, and then we reach these components. Okay? We don't exactly learn how to put these components into upper level components. That would be the next course. So here we start with transistors, reach adders, comparators. I will guarantee that you will be able to take a comparator, build a comparator. I'll guarantee that you'll be able to have a controller for a little RT level circuit. So you learn the elements of an RT level circuit. So you have a system, you have RTL subsystems, a filter, a processor, a trigonometric function, and exponential function. These are the little components, RTL subcomponents. Then you get into one of these RTL components, then RTL subsystems, sorry. You get into one of these RTL subsystems, let's say the filter. Then you look inside it, you see, oh, there is a logic unit, there is a register file, there is a counter, there is a state machine. But then I say, well, in this course, you will be able to see all of this. Okay, you will be able to build these with what? With the gates. You will be able to build gates with what? With switches. We are not going to get down into layout. We start with a little bit of transistor, go to gates, and then go to these components. Who is going to help us? If we are left just empty-handed, we won't be able to do this. We need tools. We need a computer to do something for us, analyze this circuit for us, turn the upper level description into transistor layer, into interconnection of transistors. If this is what I expect from a software program, I have to be able to communicate with that software program. I have to be able to tell that software program, hey, I need an adder. Okay? And this is the description of the adder. I have to be able to tell the software program that, okay, this adder is built out of these little gates. I have to be able to describe that. I have to be able to describe a circuit, part behavioral, part functional, part gate level, in some cases transistor level also. And then analyze that, and then eventually synthesize that. For that, I use hardware description languages. The hardware description language we'll use in this course is Verilog. Okay? And we use Verilog day one. Day one, we use Verilog. What it means is we start with transistors. We say, okay, here is a transistor as a switch, and then this is the Verilog description of it. Then we say these are gates, so this is the Verilog description of it. This is a comparator or an adder, this is the Verilog description of it. This is an RTL component, this is the Verilog description of it. So we take Verilog along with us throughout the course. As we are showing schematics, we'll be showing Verilog descriptions. As we wire schematics together, we will be showing the wiring of these schematics together in Verilog. Verilog describes the hardware at several different levels. Okay? These are not solid lines, okay? But then you can describe something functional. You can describe something behavioral. I can describe a filter by saying, let's perform these many multiplications and additions, and then this gives me the filtering. Okay? Here is a very, very simple description of an adder. Here I'm saying this is an adder. This is a 1-bit adder adding 2 binary numbers. That's all there is to it. It's not a very complex thing at all. And then I'm describing it in Verilog. You will be able to learn this description and descriptions far more complex than this and far more behavioral than this. Okay? Behavioral means that a very descriptive description is there. Here, yeah, since I'm saying it's an adder, well, I'm using an adder, so obviously it is an adder. Okay? But then some things get a little bit more complex. We will be seeing all of those. Verilog allows you to interconnect components, whether they are behavioral components or they are structural components, or you have one component within that there are many, many gates. You look at it, you say, well, this is one component. But then inside it, there are many gates. This is a component, you have described it at the behavioral level, but nevertheless, you want to wire them together. You have a system that uses that behavioral description, also that gate level description of it. Verilog allows you to do that. Okay? So not only Verilog allows you to describe something as its functional description, but also Verilog allows you to wire components regardless of how they've been described inside. So you can model RTL, you can model gates, you can model transistors, and you can wire them together. So you have this Verilog description. A part of it is behavioral. Perhaps your processor is described behaviorally. Your filter is described at the register transfer level. Maybe you have a little gate circuit here that has gates in it, ands and ors and things in it. Okay? Maybe you have another part of your circuit which is described at the transistor level. But then Verilog allows you to wire these together. This output goes to this input, this output goes to this input, maybe this output goes there, this output goes here, maybe an input comes into the gates, maybe an input goes here, this and that. The Verilog allows you to describe this. A multi-level description. Okay? A description that in some of the descriptions look very C-like description. On the other hand, some of the descriptions are very transistor description. Verilog allows you to describe this multi-level. Level meaning levels of abstraction description. Okay? So let's say I have my description. Why did I describe part of it at the transistor? Why behavioral? Why this? Why that? That doesn't matter. That was my choice of design. Nevertheless, I have to test it. How do I test it? If it was a real circuit, I would put it on my circuit, on my test bench, and then put oscilloscope and voltmeters and things like that to it. And then look at the waveforms. But see, I don't have the real circuit. I only have this model. Okay? How do I do that? I need to test it using a test bench, which I'm going to talk about. So this is my hardware description, this thing. What do I use it for? I use it for simulation. Simulation, I need a test bench. I simulate it. I verify that this is exactly what I want or not. Maybe not. Maybe this gate needs to be changed, or maybe this behavioral description needs to be changed. So I go through simulate, simulate, simulate until I look at this circuit and say, okay, this is exactly what I want. Okay, so I test it, I verify it, I look at the outputs of it. Not the actual output, but the output of my model. Okay, these waveforms, I look at this, I say, okay, it looks like this is the way it should work. I look at the output reports, simulation reports. I compare my specification of the problem with the simulation result of my design. And my design is multi-level design. I compare, and then eventually I say, yes, this is exactly what I want. What do I do now? Look at this. What do I do now? Do I take this and then take one by one transistors, wire them together, take that behavioral description and turn it into registers and comparators, and then take those into gates and then gates into transistors? No, I'm not going to do that. I'm going to take this whole description, give it to a software program which is called a synthesis tool. My verified description, this verified description, now goes into my synthesis tool. the synthesis tool, depending on the target hardware. Let's say another input is target hardware. That means, what do I want? Do I want to put it on an ASIC or an FPGA? Or how do I want to implement this? Depending on the target hardware, it will generate a netlist of those components of this target hardware. A netlist, a complete netlist, as if I had created the netlist myself, as if I had put all these gates together myself. But then I haven't done that. I have said, this is what I want. This is the behavioral description. This is the RTL description. This is this and this is this. Give it to the synthesis tool. I tell the system, okay, give me a netlist. The netlist can be the elements existing in the target hardware. Maybe gates, maybe transistors, maybe list of transistors that I feed into the layout program. Okay? Eventually, what I come up with is a complete layout of the thing. Or build the hardware into a programmable logic device, PLD. One last thing before we leave this subject is, well, how do I simulate? My circuit is not real, it's a model. I cannot take a model and put it in a real test bench. And therefore, what I have to do is also create a model for my test bench. The test bench includes scope, function generators, multimeters, equipment for measuring the outputs and all that. I have all of these, but virtually in Verilog. So the same way I take my design under test and put it on the test bench, I take my model of the design that I'm doing, which is this. I take this, and then it becomes this. It's not real, it's model. And this is the circuit I'm building. Look at it. It's a breadboard. Okay? And then I take this green circuit in Verilog and the Verilog description of it, put it in the test bench. The test bench applies waveforms to it, inputs to it, this to it, and then eventually the waveform, it comes up with output waveforms. Okay? That's why I'm saying that with this simulation thing, I have the test bench and my model, and I will be able to verify the waveform. Look at the waveform here. The waveform is virtual waveform that I will be able to see with my virtual test bench. Usually, output is a waveform or reports. For simple circuit, let's stick with waveforms. What we have done is we have talked about hierarchical system structure top-down and Verilog hardware description. We know what to expect from hardware description languages or Verilog hardware description. And we also talked about design flow. Simulate, verify, modify, and then synthesize, build a circuit, and you're done. Okay, so we'll start next time with a little bit more of the basics. But this was just overview of the thing.